Problem 3. A single frictionless roller coaster cart of mass 825 kilograms tops the first hill with the speed of 17 meters per second at height 42 meters. A. Is energy conserved or not conserved? Explain. What type of diagram is appropriate for this situation? A work energy or an energy bar diagram? Draw it. What is the speed of the car from point A to point B? And then C, how high will the car go on the last hill, which is too high for it to cross? So there are two approaches to this problem. The first approach that we're going to look at is we're going to look at the work energy theorem to answer this question. And then we'll look at it in terms of conservation of energy. I want to draw a picture of the situation. Along with a work energy bar diagram. So if I look at it this way, then what we do here is that we define the system as only the car. So when I look at this, I have something that looks something like this. Here's the bottom or the ground, and then I'm going to have a roller coaster. And as I look at the roller coaster, somewhere along this roller coaster, we have a cart. So when I look at this cart, the first thing I want to do here is that I want to isolate, I want to look at what is the system here. So if I look at the system, then what we ask is, what are the external forces? Well, the fact that we have Earth down here implies that one of the external forces has to be the force of gravity. Another force that occurs is that the railroad track has to apply an upward force toward a horizontal force, but in other words, I have a changing normal that occurs. So what we see here is that there are two external forces. The normal and gravity. So according to the work energy theorem, we have a net work that's being done. We have the work of the normal plus the work of gravity. But what do we know about this? Well, the normal force will always be zero. And the reason why is because if I have a normal force, I'm always going to be perpendicular to the displacement. So because it's perpendicular to displacement, it does no work. So the only work that occurs is the work of gravity. And this work is not zero. And because of this, that tells me that the change in kinetic energy of the car is also not zero. And therefore, the kinetic energy before and the kinetic energy afterwards are not the same. In other words, energy is not conserved. So if I write this out, we can then say from the work energy theorem that K1 plus the work of gravity is going to equal to K2, where K1 is not the same as K2. And that tells us here is that energy, in this case, kinetic energy, is not conserved. So the work energy must be used. So now let's apply this to our situation. The bar diagram must look as follows here. Picture-wise, I imagine that I have my track. So if I'm drawing my track, I see that my track goes up and down, and then it comes down, and then it comes up to half the point, and then part of the track then continues to go off. So if I look at this as being the bottom, then the track shape is then going to be this orange right here. So I'm going to call this point 0. I'm going to call this point A, this point C, and somewhere, I mean, B, excuse me, and somewhere over here is C. So what do they tell us? We have a cart here, and we're going to be looking at, it starts here at point 0, and it has some kinetic energy. So we know that it's moving in this direction with some speed 0 here. And then this cart gets to point A, and then we're going to be looking at point B. So I'm looking at 3 places here. So because these hills have the same height, the kinetic energy at point 0 and the kinetic energy at point A have to be the same. And the kinetic energy at B is going to have a speed of VB. So what they're telling us here is that if this height is H, then the hill at H also has a height of H, but the hill at B has a height of half the height. Now, if I look at the path, okay, so the path from A to B is downwards. And we expect that the speed at B is higher than at A. And the question is, why? That has to do with the work of gravity is positive work. And the reason why it's positive is because when I look at the work from A to B, look at the force of gravity, it's downwards. Look at the displacement is downwards. Since in this case, we can see here is that these two forces are parallel. And if they're parallel, that then tells us that there's an increase in, it increases the kinetic energy of the car, which then tells us that the change in kinetic energy has to be positive. So now, if I look at my bar diagram from that, looking at this, then I'm going to say that I have this one. So if I look at A, I'm going to say that A is then going to be this big. So the kinetic energy at A plus the positive work done by gravity should then cause the kinetic energy at B to be higher here. These guys should be the same quantity according to the work energy theorem. So now we have to start looking at how does this look like mathematically. So picture-wise, you can see here is that the kinetic energy at A plus the work of gravity is then going to be KB. Let's compute that. So now, using the work energy theorem, we see here is that Ka plus the work of gravity has to be Kb. So when I'm looking at this, this tells me here that this has to be 1/2 mv a squared minus mg delta y, and that has to equal to 1/2 mvb squared. So what I need to do is isolate VB to determine the speed at B. So if I do that, I'm going to take and I'm going to divide both sides by 1/2 m. So if you look at the first thing that I would note is that note that all the masses cancel out. So all masses cancel out. So this is a mass independent result. So if I solve for VB, note that VB is a squared quantity. So I'm going to need a square root. And then if I multiply both sides by 2, I'm going to get VA squared. Now, if I multiply this by 2, I'm going to get minus 2G delta Y. So when I look at this thing, what do I know? What do I know about the height? The final height is the height at YB, and my initial height is YA. So note, I'm going down, so I expect a negative number. So then this should be YB minus YA, and according to what we see from the picture, this is going to be 1/2 H minus H, which I get minus 1/2 H. As expected, the height change is negative. Now, if I substitute this delta Y into this quantity, you're going to see that the 2's are going to cancel, the minus signs are going to cancel, and I'm going to end up with a result that looks something like this, plus GH. So when I look at my values, they tell us that VA is 17 meters per second, and that H is 42 meters. So if I plug this into this quantity here, I'm going to see that I'm going to get 17 meters squared plus G, which is 9.81 meters per second times 42 meters. Now I'm going to square root this quantity. And when I actually compute the whole thing, I get 26.5 meters per second, and that's going to be the speed at point B. So what caused the change in kinetic energy? It was the work done by gravity. Now, if I come up here and I copy this, what I'm going to see here is question B is asking how high will the car go up the last hill? So picture-wise, we have this image. Now, the only thing I'm going to focus on now is I'm going to focus between B and C. So I don't care what happened beforehand. I'm only going to focus to B. And what we should expect here is that when it gets to its maximum height, so what we expect is that at max height, the speed VC should be 0. So if that's the case, I'm going to define this as YC. That's going to be the final height. And so I'm going to look at the path. So we're going to focus on the path between B and C. Again, we've already talked about that the normal force does 0 work, but the work of gravity does do work. And the reason why this is I go from B to C, the force of gravity is downwards, but as I go from B to C, that displacement goes in the vertical direction. So we can then say that the work of gravity, WG, does negative work since the force of gravity and the displacement are in opposite direction. That immediately tells us that there's a decrease in kinetic energy of the car, which then tells us that the kinetic energy has to be less than 0. So if I look at my bar diagram, it should look something like this. So now, the bar diagram says I start off with this amount of kinetic energy. Let's say I have that amount of kinetic energy right here. And this is the kinetic energy at B. So now, what does gravity do? It has to change this kinetic energy in such a way that the work done decreases the kinetic energy to be 0. So then from the work energy theorem, it tells me that the kinetic energy at B minus the work of gravity, this work changes the kinetic energy to be 0. So now we can use the work energy theorem to calculate this height C. So from the work energy theorem, the height YC is given by the work energy theorem that then says that KB minus the work of gravity is equal to 0. So if this is 0, then this tells me here is that then KB here must equal the work of gravity. And in this case here, it has to be what? This is going to be mg delta y, which will then be mg yc minus yb. So when I put this all together, which I realized I did not write this in, I should have written something like this a little bit clearer. Let me move this over to the side. That then what this tells us here is that this should be 1/2 mvb squared is then going to equal this quantity. And when you look at this thing, once again, you could see that the mass cancels out. So now, isolating YC, we could see here is that YC is then going to equal to YB plus VB squared divided by 2G. So if I look at that, I can see here is that then YB is then 1/2 H, which is 1/2 times 42 meters, which is 21 meters. And then VB, which is a number we already calculated, is 26.5 meters per second. So if I plug in these values here, I'm going to get 21 meters plus 2 times 9.81 meters per second squared. And then up above, I'm going to get 26.5 meters per second squared. And that number gives me 56.8 meters for the height of YC relative to the ground.